Everybody, good evening and welcome to the Sigma meeting for February 2023. January seemed to be a long month, but it seemed to have gone very quickly, if that makes any sense. All right, so I want to start off. So my name's Pete Sherman. If you don't know me, I'm the chairman of Sigma and I'll be your host for the evening. And I would like to not just welcome Sigma members who joined us tonight, but also our affiliated club members as well. That's the likes of Highland Astronomical Society, Aberdeen Astronomical Society, Caithness Astronomical Group, North Ronaldsea, and I believe we got a few people here from Dundee tonight as well. Also, a very special welcome to some of the new members and first-time visitors. We have got Gareth Brown, John Sinclair, Tina Cowell, Alan Bartley and Graham Middleton. You're very welcome and I hope you enjoy the evening. Just a little reminder before we go on too far about your subs for this year. I did mention it last year, but as I say, I know a lot of you like to pay at the meeting, but as our next meeting isn't until April, it would be handy if you get your subs for 2023 into MIC a little bit sooner by doing that by bank transfer if you can. It just keeps us right on the regulations for GDPR. Otherwise, we've got to do a little bit of messing around and just makes mixed life a little bit hard. That's all. Okay. Right, on with the meeting. So in the background now, we've got Mick and Rich, who are the Zoom co-hosts, who will keep things running if anything technical goes wrong with me, which it did just now. You may have noticed I just cut out for some unknown reason. I don't know why, but I managed to get back in quick enough to get everything running again. But we have got a backup should that happen again. Mick will be doing the Moray Sky at Night in the second half, and Rich will be handling your questions and answers. And I'll just go through a little bit of the Zoom controls for the new visitors. You may not have used, well, I think we've all used Zoom over the last two and a bit years, but just how we work it here. If you've got any questions for Martin tonight, if you can put them into the Q&A, in the toolbar at the bottom, you'll see a little button that says Q&A. If you can put your questions in there, you can do it any time throughout the talk. Rich will then keep an eye on them and he will ask them over to Martin at the end of his talk. Okay, there. And you'll see you've got the chat box there. I see a little bit of chat going on. That will be turned off during the main talks. It gets a little bit sort of distracting. We keep getting these pop-ups coming in when the speakers are trying to do their presentation, but we'll go back on during the break. So you can have a chat to everybody for a little while in there if you wanted to, and then join the break. They say, don't go putting your questions in the chat because it does move very, very fast and it's more than likely your question's going to get lost. Okay, there. And if you've got any issues at all, just click the raise hand button that's in that toolbar as well. We'll see your hands gone up and one of us from, on the panel will come over and ask you what the problem is through the chat because we can do it privately in the chat and it doesn't disturb the speaker. Okay, so on with the meeting as for tonight. As I say, the way it works, the Sigma meeting, we have the main talk, which I say tonight is by Martin Hendry. Q&A, as I say, will be handled by Rich. We then have a little 10-minute break, just gets us time to get set up for the second half and give everyone a chance to stretch their legs a little bit. We've got some members' photos then in the second half. Then we'll have more Sky Night with Mick and a little bit of club news for me to finish off with. We look at finishing around about 9:30. But like I always say, we're not sticklers for time here and it's cloudy outside, so we're not rushing out to get the telescopes out tonight. Okay, so it's wonderful to welcome back Professor Martin Hendry. Martin is a professor of gravitational astrophysics and cosmology at the University of Glasgow, where in 2022 he was appointed vice principal and clerk of Senate, having previously been head of the head of the School of Physics and Astronomy between 2012 and 2020. Prior to his faculty appointment at Glasgow in 1998, he was a research fellow in the Astronomy Centre at the University of Sussex. Martin is a senior member of the LIGO scientific collaboration, serving as divisional head and member of the LSC management team between 2017 and 2022. And also held leadership roles within LISA and the Einstein Telescope Consortia. Martin is a Fellow of the Royal Society of Edinburgh and the Institute of Physics, and throughout his career, he has been a passionate advocate of STEM, education and outreach. In 2015, he was awarded an MBE, which I didn't know that until I read this, Martin. Congratulations, for his services to the public's understanding of science. But more than that, Martin is a great friend of Sigma and a thoroughly nice bloke. It's a shame, you can't get to meet him in person because you would agree with me. He's given many talks with Sigma over the years. I think we've worked out as 7, but Tim will say a bit more about that, I think, later on. And I say he's done many talks for Sigma over the club's existence, which just go to show his keenness in supporting the astronomical world, the amateur astronomical world, in fact. So with that, it gives me great pleasure to welcome back for the umpteenth time, Professor Martin Hendry.
Thank you very much, Pete, for those kind words. Let me share my screen in the time-honored fashion. We've all got much more used to this over the last few years. So hopefully it will all work seamlessly.
Yep, that's up.
My title slide, I'll just maximize it to full screen, and then I think we're good to go. Excellent. So real pleasure to be back talking with you. Of course, I look forward to the chance to visit in person. But even before COVID, one of the times that I was scheduled to come northwards and visit, I remember having to call off because of snow and rain and all sorts of horrible weather. The really ironic thing is I seem to recall that was a May talk, not a February one. So it just goes to show you what the Scottish weather can sometimes throw at us. But nonetheless, with COVID, it's opened up the possibility for what we're doing tonight, which is to be able to share my talk online. And it's great to hear and to see that there are so many friends and colleagues from other astronomy societies as well. So over the course of the next 45 minutes or so, I'm going to give you a bit of a whistle-stop tour through the last 100 years or so of research into gravitational astronomy, but in particular focusing on the last 7 years since we announced the first ever detection of gravitational waves. So if you don't know what gravitational waves are, never fear, that's what I'm here to help explain. And indeed, if you hadn't previously heard of the LIGO scientific collaboration, then I'll say a little bit about that as well. So this first slide has been largely covered by Pete, and I'm very grateful for his words of introduction explaining my various roles. So it was only just a few months ago that I was appointed Clerk of Senate and Vice Principal, gradually adjusting to that role. My office is now up in the, what you might term the Hogwarts part of Glasgow University campus, and it's a real pleasure to be taking on some additional responsibilities. But I'm doing my very best not to lighten up too much on my astronomy work. In fact, this is the 4th talk I've done this week alone to a variety of audiences, everything from our undergraduate student society, they wanted to hear about the physics of Star Wars, to doing a colloquium in Edinburgh on Wednesday, and then another talk on Tuesday evening as well. So great to round off the week with a talk for Sigma. And I just thought I'd say a little bit about what gravitational astrophysics and cosmology is in essence all about. The gravitational astrophysics part reflects the fact that a lot of the phenomena, some might say most of the phenomena that we study in the universe, have a great deal to do with gravity. Gravity is what makes planets orbit stars and stars orbit within their galaxies, and indeed it plays a large part in affecting how galaxies behave. But also, as we have realized for about the last 100 years, it isn't just gravity that's the end of the story, because our universe as a whole is actually expanding. And I know I've talked to Sigma before, I've talked to a number of the other societies in recent years about that fascinating story of how our attempts to measure the expansion of the universe have made progress for sure, but in some respects, we're still scratching our heads a little bit when it comes to measuring just how fast the universe is expanding. So that's one of the themes I'm going to talk about tonight in the context of gravitational wave astronomy. So what exactly is gravitational wave astronomy? So it's an aspect of gravity which is very firmly part of Einstein's picture of gravity. So we're going to begin my talk by looking a bit at that, where Einstein's ideas came from and how they give rise to the notion of gravitational waves, which are a different form of radiation altogether from the electromagnetic waves, the light waves that we've been accustomed to studying in astronomy for, well, hundreds of years in the case of optical light, and a good part of a century in terms of other parts of the electromagnetic spectrum. And gravitational waves, as we will learn over the course of the next few slides, are produced by some of the most extreme and violent events in the universe. Things like exploding stars or colliding black holes, or indeed possibly from the birth of the universe itself. So although they are part of a prediction of Einstein's theory of gravity, which, as we'll see in a few minutes, has been around for more than 100 years, it took us essentially 100 years to develop the technology capable of detecting gravitational waves. So I probably won't have really enough time to do that part justice. And, you know, it deserves almost a talk in itself, how we developed the sensitive detectors capable of detecting these gravitational waves. But in some respects, although that is in itself a fascinating story, it was always just designed to be the prelude to opening a whole new way of studying the universe. And therefore, to allow myself enough time to share what we've learned through opening that whole new way to study the universe, forgive me if I compress a description of how the detectors actually work into just a few minutes. So more on that coming up very shortly. But let me, before we start to look at the detectors themselves, just say a word about how this organization, the LIGO Scientific Collaboration, takes shape. It's truly a global collaboration. It's in some ways a product of the National Science Foundation in the US, and in particular, the creation by the NSF of two giant observatories. But they're very different from optical observatories or other types of astronomical observatories studying light. These are detectors sensitive to these gravitational waves that I've mentioned, and they're in fact lasers. They're based on lasers, and hence the L in LIGO stands for laser, and it's Laser Interferometer Gravitational Wave Observatory. So you can see a kind of cartoon of one of those in the left-hand side of this slide. I won't dwell on that for now because we are going to look briefly at how laser interferometers work in a slide or two's time. But what this slide is just giving you hopefully a sense of is the truly global nature of the collaboration. We have groups all around the world, a big concentration in the US, but quite a number in Europe, in Asia, in Australasia. Thus far, none in Africa. And I was very proud to be invited to take part in the Oman Science Festival in October of last year. And it's clear that there is growing interest in the Middle East and indeed in sub-Saharan Africa in fundamental astronomy. Some people might know about the Square Kilometre Array radio telescope, which is going to be located in Southern Africa and in Australia. So we hope that in the future, we'll be able to extend our gravitational wave collaboration to some of those other parts of the world where right now astronomy has a presence, but not gravitational wave astronomy. But for the moment, we've got a very impressive number of institutions who are part of the collaboration. And one of my jobs when I was division head for communications and education was to look after this PowerPoint slide. In the bottom right, you can see the logos of all of our partner institutions. So the more institutions that join, then the harder it becomes to fit all those logos onto one slide. But that's a nice problem to have. And we're currently sitting at about 80 institutions across the world and more than 1,500 scientists and engineers who are part of the LSC. And in fact, the LSC is in itself just one partner in an even more global, in some sense, scientific collaboration when LIGO was working with Virgo and CAGRA. Virgo and CAGRA are two other gravitational wave detectors, and we'll talk a bit more about them later on. So that's a little bit about LIGO, and I've already mentioned Einstein, so let's dig in a bit more to Einstein's theory of gravity. I love this slide. It's quite a few years old now. It's a photo of me from the mid-2000s, but it's from the statue of Einstein at the National Academy of Sciences in in Washington, DC. And whenever I'm in DC, which I haven't managed for a few years now because of COVID, but I always try to visit this statue. I love the way that it depicts, you know, that classic view of Einstein as the wizened old scientist. But it's beautifully sculpted, and on the statue, he's holding his notebook, and there are 3 equations there. So I wanted to mention this partly to reassure everyone that this isn't going to be one of those talks that's full of equations. So don't panic if equations aren't your thing. But I imagine everyone's probably heard of E equals mc squared, Einstein's famous equation that relates the energy of a body to its mass. And c in that equation is the speed of light, 300 million meters per second. So that's a very big number. And if you square it, it's an even bigger number. So that idea of there being a lot of energy associated with a relatively small amount of mass is one of the key ideas of Einstein's theory of relativity that he developed in 1905. And it was one of the things that propelled him to global fame as a really, truly outstanding scientist. The other 2 equations on the Einstein statue also are part of our story in a sense. The middle one relates to the properties of lasers. And as I mentioned, with the L in LIGO standing for laser, then that's going to feature in our story in a moment or two as well. And that equation is to do with what Einstein actually got the Nobel Prize for, which was his work on what we call the photoelectric effect, to do with the way that packets of light energy called photons can be ejected from atoms, or indeed, what can also happen is that when you shine a beam of light containing photons on an atom, it can cause changes in the energy of the electrons within that atom. So ideas like that underpin the physics of how lasers work, and we'll see very shortly how important lasers are for LIGO. But just before we set our equations aside, the final one to mention on the statue is the very top one. And that's frankly a bit scary. Even if you could read the details, it might not mean terribly much unless you've had the sort of the grounding in the necessary maths to understand what Einstein's general theory of relativity is all about. But again, don't panic. We're not going to concentrate on the mathematical description. We're going to instead largely deal in terms of analogy and some good solid pictures thrown in. And many of those you might already be familiar with, because the idea of Einstein's general theory of relativity is that gravity is nothing more than the curvature of space and time themselves. And well, you know, that's in a sense what you might argue really made Einstein's name. He didn't get the Nobel Prize for that, but it is the theory that's regarded as his masterpiece, a theory of gravity, a theory that explains gravity in terms of the curvature of the very fabric of space-time itself. And that led Time magazine in the year 1999, their editorial board made the decision to award Einstein the title of Person of the 20th Century because of the impact of his science, partly his general relativity, a little bit as well, his work on lasers, and well, actually, the laser part came much later, but he laid the theoretical foundations that would lead to lasers in terms of the area of physics that we call quantum physics. So these 2 big contributions have a large part to say in our story tonight: general relativity, his theory of gravity, and the theory of quantum physics, which underpins the operation of the LIGO detectors. So all of that, I think, means that Einstein merits that title of Person of the 20th Century. That wasn't even just scientist of the 20th century, it was overall the most influential person of the 20th century. Well, let me stress, though, that was the editorial board's decision. There was also a public vote, and the public voted for Elvis Presley. So you can judge for yourself who got that one right. But when it comes to Einstein's science, it's important perhaps to also remember, however, that the wizened old figure with the white hair and, you know, the sort of shock of hair, rather unruly, that's very much late career Einstein, just like depicted on the left-hand side. And actually his development of ideas about quantum physics and relativity was relatively early in his career. And the Einstein who proposed his general theory of relativity looked rather more like the chap on the right. This was all done in the early years of the 20th century, between 1905 and 1915. Einstein would go on to live until 1955. So he had many, many years after he came to fame through his theories of relativity. So let's just say a little bit about what general relativity is all about. I've said that it's a theory of gravity, and where Einstein developed it from was his fabulous ability to ask awkward questions. He was very good at challenging the scientific orthodoxy by asking just the right question that got to the nub of a problem. And in the context of gravity, it was very much to do with how gravity actually propagates through empty space. Ever since Isaac Newton, we had this picture of the moon experiencing a gravitational force from the Earth, and that balances an outward force due to the moon's circular orbit around the Earth. So you've got the force to do with the circular orbit, a circular acceleration, and then that's balanced by the gravitational force pulling the moon towards the Earth, and that keeps the moon in its orbit. So from a mathematical point of view, that all works beautifully. And even from a physics point of view, for high school physics and even much of our undergraduate teaching, that's the way that we might typically describe gravity. We do it in terms of forces. But what Einstein had to say about the matter was that, well, this is deeply unsatisfactory because it doesn't explain how the force gets from the Earth to the moon. How does gravity act at a distance across empty space? So to try and answer that question, Einstein really went back to square one. And he went back to a picture of gravity that throws out the notion of the force altogether, and instead thinks of gravity as really embedded in the fabric of space and time. There's a neat phrase, not due to Einstein himself, but due to John Wheeler, a scientist who came a little later. And Wheeler described Einstein's theory of gravity, his general relativity, that was published in 1915. He described it in these terms. He said that it's all about space-time telling gravity how to move, and matter telling, oh, I'm sorry, I said that wrong. You think I'd be able to read my own slides. It's been a long week. Space-time tells matter how to move, and matter tells space-time how to curve. So this relationship between the presence of matter and indeed energy in the universe and the curvature of the very fabric of the universe, that's what general relativity is all about. And you may have encountered these ideas in a variety of forms. You've even heard me talk about them before. But a good picture for all of this, it's not perfect, but I think it conveys a clear metaphor for what's going on, is to think of space-time as like a stretched sheet of rubber, like a trampoline. And if you take a massive body and drop it onto that trampoline, then it will cause the rubber sheet to bend. And that's really the manifestation of gravity that Einstein's theory gives us. Instead of thinking about a force reaching out from the Earth to the moon follows the natural curved space-time that's induced by the mass of the Earth warping the space-time around it. And that's why the moon follows its orbital path around the Earth. So straight away, that opens up possibilities for gravitational waves. So let's see if we can get our head around that next. Firstly, let's just pause for a moment to think about the electromagnetic spectrum. So there's the visible light that we have with which we've been able to study the universe really since the dawn of time, but with telescopes for several hundred years. In 1609, Galileo first turned his telescope on the heavens and saw all kinds of things that we didn't know about before, like the moons of Jupiter, the rings of Saturn, the craters of the moon, and so on. And then for about 100 years, we've become aware of a much broader spectrum of light. The theoretical foundations of that go back to the mid-19th century with James Clerk Maxwell. And then a few decades later, we began to understand how we could not only observe, but indeed in some cases create different forms of electromagnetic radiation, like radio waves, for example, but then going all the way to gamma rays and X-rays The gamma rays and X-rays have very short wavelength, the radio waves have very long wavelength, and the visible light that our eyes can see is somewhere in the middle. But general relativity predicted a whole new type of radiation, a new window on the cosmos, what we're referring to as gravitational waves. So what exactly are they? Well, if we think of that stretched sheet of rubber analogy again, then if you drop a massive object onto a trampoline, the trampoline is going to wobble. And that essentially is what we're talking about when we introduce the idea of gravitational waves. We're talking about the wobbling of space-time caused by changing gravitational fields. Now, strictly speaking, that means when I wave my fist, I'm generating gravitational waves because the matter in my hand is changing its position. I'm accelerating my hand back and forth, and that, according to Einstein's general relativity, should produce curvature of space-time. It should produce space-time ripples that spread out from my hand. But my hand doesn't have a mass comparable to that of a star, and I'm not moving it anywhere near the speed of light. And what you learn from looking at the numbers in Einstein's theory is that to produce measurable gravitational waves, we need to shake up space-time with stellar mass objects moving close to the speed of light. A bit like in the cartoon here. Okay, they're not moving close to the speed of light, but what we're depicting here is two compact stars like neutron stars, or we'll shortly talk about black holes, orbiting around each other very close together. That's the kind of disturbance in space-time that would produce ripples, gravitational waves, that are strong enough to give us a chance of detecting them. But it's still an enormous challenge because the disturbances correspond to, by the time the gravitational waves reach us, a distortion of our patch of space-time equivalent to about a millionth the width of a human hair, or about 1,000th the size of a proton in the nucleus of an atom. So how on earth are you going to measure a disturbance in space-time that weak? Well, on Earth is the kind of operative term there, because the challenge isn't just that the signals are so incredibly weak, it's also that there are many other sources of disturbance that could completely swamp that signal. And yet, remarkably, this is what the LIGO interferometers can do. They can detect those tiny, tiny signals despite them being so minute compared with some of the local disturbances that would shake up the Earth in a more conventional manner, but such that they could potentially swamp the signal we're looking for. So LIGO, Laser Interferometer Gravitational Wave Observatory, these facilities are located in Louisiana. It's the one shown in the right, and Hanford, Washington, shown in the left. And these are 3,000 kilometers apart in the US, and the arms of the L-shaped laser interferometer are 4 kilometers long. So what exactly is a laser interferometer? So here's a short cartoon of that. What it does is it produces a beam of laser light. Well, it's represented as a wave, but perhaps more correctly, we should really think of the laser light as a stream of photons, like I mentioned a little earlier. But it's perhaps easier, I think, to see, to visualize what might be going on by representing the light as a wave. What we see is the light beam traveling along two perpendicular arms and bouncing off mirrors at the ends of those arms. And then when the light is reflected back, the light's recombined and then output to a detector. And crucially, what's happening, if we watch the video again, we can see that during all of that taking place, then there's a gravitational wave passing by. And what that effectively does is to stretch and squeeze the length of the two arms of the interferometer. So it means that the laser light is traveling a different distance along one arm compared with the other, or because of the constancy of the speed of light, which is another key idea in Einstein's theory, you can equivalently think of it as the laser light takes a different time to go along one arm and back compared with the other arm and back. And that's where the I in LIGO comes in, because it means that when the laser light arrives back at the central mirror, the beam splitter, and the two beams are recombined, then they've traveled a different path. They've got out of step with each other, or out of phase with each other. So we get an interference pattern. So it's a laser interferometer, because you're taking laser light, you're looking for interferometry to happen, interference between the two laser beams. And if an interference pattern is observed, then that's the hallmark of the passage of a gravitational wave. But of course, other phenomena can cause changes in the arm length as well, or changes in the distance that the laser light has traveled. For example, even just the laser beam colliding with a few stray molecules in the arms, that could deflect the path. So these are held at very high vacuum, and also the mirrors are suspended to prevent them being susceptible to local ground shaking, seismic noise. So there's a great deal of instrumentation development that took place in the decades leading up to the present day. And as I mentioned at the beginning, I'm not really going to do that justice. I'm not an expert in it anyway, but there just isn't time to really do justice to what an amazing achievement building these detectors was. But it wasn't just about the instrumentation anyway, because the other aspect of it was developing a better understanding, theoretically, of what kind of signal we ought to be looking for. And that unfolded as well over the course of the 80s, the 90s, the early 2000s. And we reached a point by about the mid-2000s where we could predict theoretically what the disturbance in space-time, the gravitational wave signal, would be when you had something like two black holes colliding. So that's what's shown in the cartoon movie in the bottom left. It's just representing the black holes spiraling in towards each other, getting closer and closer together, and shaking up space-time more and more as they do. And what that does is distort space-time by a pattern that's represented in the graph. We call this a chirp. You can see that the cycles, the sort of sinusoidal variation, they're getting closer together. So that means the frequency of the wave is increasing. And also the strength or the amplitude of the wave is increasing. So that's the vertical extent. And then it reaches its maximum when the two black holes collide. And then you've now just got one black hole. Space-time wobbles a little more as things fade away, as they damp down. We call that the ring down. So you've got the in-spiral phase, the merger, and the ring down. So our theoretical understanding of all of that, how that unfolds, came on leaps and bounds through in the decades preceding the mid-2000s. And a good analogy here, I think, is to think of, well, this is a not too familiar scene these days because of COVID, but back before the pandemic, when I would more regularly do schools talks, you would sometimes find yourself in a school cafeteria at lunchtime, and frankly, it was pretty noisy in there. It was bedlam, you know, trying to hear yourself think over the background noise from all the students. And, you know, nothing wrong with that. They've got to let off some steam at lunchtime. But I guess if even one of the students is having a conversation with their friend, it might be quite hard for them to hear what's being said. But if they've got a good idea of what their friend is saying, then it's a whole lot easier to work out what the details of the conversation are. We're very good at filling in the blanks. So for me, that's quite a good analogy of the difficulties of searching for gravitational waves. It's difficult enough anyway because of all the background noise. But if you know what signal you're looking for, in other words, if you've done all the theoretical heavy lifting and worked out what the waveform pattern should be, then it makes it a lot easier to detect that even when you've got a noisy background. So that's kind of where we were in the mid-2000s. We'd made the theoretical developments to understand the waveform predictions, and we were starting to put in place the technology to build really sensitive detectors. But then the next step was to move to more advanced versions of those detectors that were even more sensitive. A bit like somebody going into that, you know, cafeteria and saying, shh, suddenly the noise gets quieter, and then you can hear the conversation in your immediate vicinity a whole lot more easily. So in 2010, upgrades to the LIGO detectors began to convert them to advanced LIGO. And the idea was principally to focus on reducing the background noise from seismic disturbance. That means to isolate the mirrors more effectively from their surrounding environment so that they wouldn't shake so much. And that produced amazing results. So you've probably heard this before. I may even have shared it in my talk in 2017, because this is quite old news now. We're very shortly going to get on to much more up-to-date discoveries. But let's just take a moment to look back at that first detection. We announced it on February the 11th, 2016, almost 7 years ago, and the event itself occurred in September 2015. It was just a few days after the LIGO detectors had been fully upgraded to advanced LIGO, with better seismic isolation. In fact, the UK had a major role in all of that. And within the UK effort, Glasgow, our research group, had a leading role. And the purpose was, as I said, to reduce the background noise by replacing the steel wires that had previously suspended the mirrors by silica fibers, incredibly delicate glass fibers, basically, that were much less susceptible to all of that seismic and thermal noise. So what we got is what I've just played, which is a signal that was observed on September 14th, 2015 in the LIGO Hanford and LIGO Livingston detectors. Even though they were 3,000 kilometers apart, the similarity of the signal told us immediately that we were onto something. But it took us 5 months to carefully check and recheck and triple check that we had really got a true cosmic signal and not just a manifestation of the local noise. And the other thing I've done with that short video is we've converted the gravitational wave pattern into sound. Gravitational waves are not sound waves, but the frequency range that the LIGO detectors are most sensitive to corresponds to frequencies that the human ear can hear. So we can render the gravitational wave data as if it were sound. And what you hear, it's not so easy to hear, but I'll play it again and you can listen. You hear a pattern that we call a chirp. So I'm cheating a bit in two ways. I'm playing it over and over again because the actual chirp only lasted for about 1/3 of a second and then it was gone. And I'm also shifting the frequency. So firstly, you hear it in the actual frequency range, and it sounds like a bit more like a low thud, and it's really very hard to make out any detail, but then shifted to higher frequencies, analogous to, if you think of, say, a false color image in optical astronomy, then you can hear the rising frequency and rising amplitude, which is also depicted visually by the blue and orange curves, and then represented a slightly different way by the sweeping curves above them. So all things considered, this was really a wonderful stroke of luck from the universe that we got such a strong event only a few days after our detectors began operation in their advanced configuration. But it wasn't entirely down to luck, because the improved sensitivity in the low frequency range that had been achieved by replacing the steel wires by glass fiber wires, that had opened up our sensitivity to precisely this type of event. So what exactly was the event? Well, we announced that in February 2016, as I said, and in fact, what that first event transpired to be was the collision of two black holes with masses about 30 times the mass of the sun. So prior to the upgraded detectors, we would not have been able to detect events like that unless they were very close to the Earth. So the upgrades had really been a game changer. And in a sense, it wasn't too surprising that within just a few days, we detected an event, because we would have been able to detect lots like that if we just had that increased low frequency sensitivity from the previous searches. So by analyzing the pattern, we were able to deduce the masses of the black holes and also how far away they were. And all of that, well, let me just pause for a minute. And let me turn over now to my colleague Laura Nuttall, who's a faculty member in the Institute of Cosmology and Gravitation in Portsmouth, another fellow member of the LIGO collaboration. And this is a short animated film that just briefly describes how we can determine distances and masses from our data.
On the 14th of September 2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
So that's just in a matter of a few seconds summarising how all of those 5 months of effort played out. Of course, it wasn't just done by eye, it was done by computer, it was done in a much more objective and rigorous way, but essentially it comes down to this. It's about matching the predicted pattern to the observed data. And that's what we were able to do and then announce in February 2016 that first detection.
On the 14th of...
And it really was quite an amazing event. Firstly, it was very far away, or as George Lucas might have put it, we were seeing something that happened a long time ago in a galaxy far, far away, more than 1.3 billion light years away, in fact. So the gravitational waves had been traveling towards the Earth for more than 1 billion years, just waiting for our detectors to switch on with the required sensitivity to pick them up. And here's an animation that we showed in the press conference back in 2016, depicting how, as the black holes spiraled in around each other and then merged, there was a burst of gravitational waves released just at that moment when they merge into a single black hole. In some ways, you might think of it, if we go back to that rubber sheet analogy, that the disturbance is so great that it sort of punctures space-time, and space-time releases a burst of energy, and then the curvature of space-time reorganizes itself into having only one dimple rather than two. Now, that burst of energy in just about 1/3 of a second released the equivalent of 3 times the mass of the sun. That's 6 million kilograms. And E equals mc squared, if you remember that from the Einstein statue, tells us how much energy that corresponds to. And since it was all released in about 1/3 of a second, you can divide the energy by 0.3 seconds and get a crude estimate of the power associated with the gravitational wave burst. Now, power, that's in units of watts. That's the same unit that we use to describe luminosity, like the luminosity of a star. But there you're talking about electromagnetic radiation. We talk about how luminous the sun is. Here, we're talking about luminosity in gravitational radiation. And there would be no light given off at all from these merging black holes. So in some sense, we're probing the dark side of the universe. And I think it was Darth Vader that said, you should never underestimate the power of the dark side of the universe. And that little calculation maybe helps to prove his point, because the luminosity and gravitational wave power of that merging pair of black holes released about 50 times more gravitational wave power than the combined light power of every star in every galaxy in the entire universe. That's how much energy is locked up in the fabric of space-time, waiting to be released when something as violent as 2 black holes collide. So, as many of you will know, that was awarded the 2017 Nobel Prize for Physics. So that announcement was made just a few months after my visit to Sigma to give the lecture in the summer of 2017. It was a very exciting summer because a number of other things happened. In particular, in August 2017, a 3rd detector joined. That's the Virgo detector, also now upgraded to Advanced Virgo. And having 3 detectors was extremely useful because what it gives you is the capability to determine where on the sky the gravitational waves have come from. Each pair of detectors can locate a source, roughly speaking to a ring on the sky, because every point on the ring corresponds to the same time delay between the arrival of the gravitational waves at one detector compared with the other. So if you have only 2 detectors, there's a ring, and you can't really pin the position down any better than that. But if you've got 3, then that's 3 different pairs, each of which gives a ring in the sky, and where those rings intersect, that's where your source is. So within just 2 weeks of Advanced Virgo beginning operation, we had already profited from that 3rd detector in the following way. We had another pair of black holes that was detected on the 14th of August, 2017. And that was localized to about, well, 60 square degrees on the sky. That's still quite a lot of sky, about maybe 300 times the area of the full moon. But that was 10 times smaller than the sky localization of the previous events that had been detected, including the very first one that we were talking about a few minutes ago. So much better sky localization comes from having multiple detectors. And then just 3 days later, in what's probably the most exciting week of my professional life, we had another spectacular event. Now, bear in mind that on August 21st of that year, there was a total solar eclipse of the sun. And I was in the US and managed to see that over there. And that was only the 2nd most exciting astronomical event for me of that week, because 4 days earlier, what we had was an event that wasn't this time 2 black holes colliding, but 2 neutron stars. That meant we detected both gravitational waves and electromagnetic radiation. And therefore, it opened up a whole new way of doing astronomy that we call multi-messenger astronomy, where we observe the universe in different messengers, gravitational waves and electromagnetic radiation in this case. So this detection was really spectacular too. Again, it's quite a few years ago, so you've probably heard quite a lot about this too, but let me just briefly recap, and then we'll move on to much more up-to-date news as well. So I'm going to play a short video first of all. So that was representing as a sound wave, the gravitational waves again, just like we did a few minutes ago with the first detection. But notice how the signal lasted for a lot longer. And the longer the signal lasts for, if you remember Laura's video, then the less massive the objects are. So that's really how we know that they were neutron stars. But the way we confirmed that they were neutron stars is that about 1.7 seconds after the gravitational wave event peaked, we got that ping that corresponded to a burst of gamma rays that was detected by the Fermi satellite and also the ESA integral satellite. And those gamma rays seem to come from the same direction on the sky as well, as this animation is showing. And there were only a few dozen galaxies in that patch of sky. So optical astronomers were able to follow that up over the 24 hours after the event. In fact, they carry on observing for many months, but during that first 24 hours, we found an optical counterpart of the gravitational wave event. That's known as a kilonova. And well, the radiation was coming out in all forms of electromagnetic radiation, the gamma rays producing what's represented in this artist's impression, the kilonova, a little bit like a dimmer version of a supernova seen in optical and infrared. There's radio emission as well. And of course, it all kicked off with the gravitational waves. Now, those observations, so here's the little optical counterpart, sparked a huge amount of activity during that week in August. So there's a before and after photo. That, of course, told us what the host galaxy was, and we could pin down from that host galaxy some key information that we could then use to measure how fast the universe was expanding. So these observations were carried out with many, many telescopes around the world, and they led us to be able to estimate what we call the Hubble constant. The Hubble-Lemaitre expansion of the universe, named after Edwin Hubble and Georges Lemaitre, is something we've known about for nigh on 100 years. But we still haven't managed to pin down just how fast the universe is expanding as precisely as we would like. Now, when I was a student, there was a more or less factor of 2 uncertainty. The units don't really matter, but some astronomers said it was expanding at 50 kilometers per second per megaparsec, whereas other astronomers said it was closer to 100. Now, the uncertainties narrowed considerably over the last 30 years thanks to the Hubble Space Telescope, but a degree of discrepancy still remains. And what we see in the bottom right is a representation of that. So before we talk about the strange looking curve, the green and orange vertical bands represent our best guess for the Hubble constant measured two very different ways. One uses the cosmic light from soon after the Big Bang and then kind of extrapolates to the present day. And the other method uses nearby stars like Cepheid variable stars or supernovae to get, you might say, a more direct local determination of the Hubble constant. So the local method is the orange band. The more distant method, extrapolated to the local equivalent, is the green band, and they don't agree with each other. So this has come to be referred to as the Hubble tension, and it's a bit of a mystery, frankly. We don't quite know what's going on there. The strange blue curve is our estimate of the Hubble constant using this totally different method, using a distance determined from gravitational waves and using the optical counterpart to determine the redshift, as we call it, how fast the host galaxy is moving away from us. So from a single observation, we were never going to settle this discrepancy of the Hubble tension, but at least we're in the right ballpark. And in the final part of my talk, I want to bring us up to date and look at how those measurements of the Hubble constant using gravitational waves have taken a big step further forward. So just something to mention along the way is that in 2018, we published our first catalogue of gravitational wave events. That included the binary neutron star that we've just been talking about and 10 binary black hole mergers. And then that immediately was giving us a much richer picture of the gravitational wave universe. We were detecting lots of black hole mergers, this very special neutron star merger, and already we were seeing more black holes in gravitational waves than we found out about, at least for stellar masses, indirectly from electromagnetic observations. So our field was really burgeoning at this point, the 2018, 2019 mark. And then in 2019, after completing more upgrades to make the detectors even more sensitive, we switched on again on April the 1st, 2019, and we began detecting lots more events. We ran for about a year. We had to stop a little early because of COVID, but by the end of that year, we'd accumulated many, many new detections. And in fact, along the way, what we were doing was sharing information about those in real time, rather than keeping it all top secret. We wanted everyone to know that there were candidate gravitational wave events so that astronomers could look with electromagnetic telescopes as quickly as possible for any signs of a counterpart. And in fact, our colleagues in Birmingham, the Birmingham LIGO group, they put together a nice app called Chirp that you can get from Google Play or the App Store, and that would give you alerts in real time about new gravitational wave events. So by the end of our third observing run, that's the one that began in April 1st, 2019, the number of events that we'd observed had really jumped a lot. We split the third run into two parts, and altogether by the end of the second half of the third run, we had 90 confirmed confident detections. And let me just mention very briefly a couple of special ones amidst that total of 90 events. There was another pair of neutron stars, so that's depicted by this artist's impression down here. We didn't see any electromagnetic counterpart that time because it was a lot more distant. I guess it just really brought home to us how lucky we had got with the binary neutron star merger we observed in 2017. But we were very confident this was a pair of neutron stars as well, because the masses determined from the gravitational wave data were not high enough to make them black hole candidates. There was another event where we weren't quite so sure of that. There was one definitely a black hole, but the lighter one maybe was a neutron star or maybe was a black hole. Now, that was our view at the time when we announced this event in 2020. We've subsequently got more sure that it was probably also a very light black hole, but more on neutron stars and black holes in a moment. We also detected a pair of black holes where one was a lot more massive than the other, and that produces a more rich pattern of gravitational waves in the signal. So it's like having higher harmonics in a musical note. So that was detected in April 2019. We announced that the following year. And then in 2020, in September of that year, we announced a really massive pair of black holes. This was detected on the 21st of May, 2019. And our announcement of that was the first time we'd announced and confirmed detection of what's called an intermediate mass black hole. So an intermediate mass black hole, well, those are really curious beasts because we don't see an easy way for them to be made from individual stars that collapse to black holes and then those black holes merge. What we're more likely talking about here is a kind of hierarchy of mergers, where two lighter black holes merge in that manner, maybe originally coming from stars, from like supernova explosions, but then those two black holes in turn combine with another two to make a bigger and more massive black hole. And in some sense, we think this is quite common because it might be a pathway by which you could make supermassive black holes that we believe are lurking at the hearts of almost all galaxies. So this was an important step towards building up that picture of how hierarchical growth of black holes might come about. And then the final kind of real highlight from our third observing run was where within the space of 10 days in January 2020, we actually observed two black hole neutron star mergers. So, you know, you wait all that time for one to come along and two come along at once. So based on the masses, we're very confident that what we're looking at is a black hole and a much less massive neutron star. But we didn't get an electromagnetic counterpart for either of them. And I'm going to run these movies again just to help explain what might be going on there. So in the top movie, what we're seeing is a simulation of what might happen if you have a black hole and a neutron star, but the neutron star gets swallowed really in one gulp by the black hole. So the gravitational wave pattern is still very rich and detailed, but what you get is the neutron star kind of disappearing into the black hole very suddenly. So you'll see that happening in just a second. And while you're keeping half an eye on that, let me start again the lower video, which is showing a somewhat different scenario. Again, neutron star in a black hole, but it's the case that the neutron star is torn apart much more slowly. Okay, it still unfolds pretty fast, but it's slow enough that the tidal distortion of the neutron star will cause a lot of debris from inside the interior of the neutron star to be strewn around the black hole to form a kind of disk of debris, an accretion disk around. So we think that the two black hole neutron star systems that we detected are more like the upper one than the lower, because we didn't see any light, as you might expect to get if there's a lot of neutron star material left hanging around as the neutron star gets torn apart. So we think this means that the black holes sort of swallowed the neutron stars in both cases pretty much in one gulp. So one way of saying that is that it means that we're talking about Pac-Man more than the Cookie Monster, where the Pac-Man would swallow the little energy pills in one gulp, whereas Cookie Monster was a bit more of a messy eater. So understanding where black holes and neutron star mergers might fit into the picture of star formation and evolution is helped a lot by whether you have a messy eater or a more sort of Pac-Man-like situation. And these are good examples of the kind of information we're going to get about black hole mergers in the future, black hole and neutron star mergers in the future. So I'm almost done. I just want to bring you more or less up to date. We announced that full latest catalogue actually more than a year ago now, but we've been continuing to do lots of analysis on it since. So there's 90 confirmed detections, and I just want to wrap up my talk by focusing on, well, let me skip this just to save a little bit of time. It's a wee bit technical anyway, but let me just talk briefly about this, because it relates to that number, the Hubble constant that we talked about before, the expansion rate of the universe. So what we've done is we've built upon the 2017 estimate. That was the blue curve that was very broad, but it was in the right ballpark to agree with more traditional estimates of the Hubble constant. What we've done since then is to fold in information from the black hole mergers. That's a bit trickier because you don't get an electromagnetic signal, so you don't get a redshift directly the way that we did for the neutron star merger. But if you pinpoint the gravitational waves as coming from a number of possible galaxies, then what you can do is average over the redshifts of all of those candidate host galaxies. And that gives you an estimate of the redshift for your gravitational wave event. And if you can do that for enough gravitational wave events, then you might hope to get a decent number out for the Hubble constant in the end. And that's more or less where we are. So what the diagrams on the right are showing is sky maps where the gravitational wave events were. And some of them weren't very well localized in the sky, but some were a lot better pinpointed. So the ones that were well localized, you can compare with surveys of galaxies and then essentially do this averaging process over all the galaxies that potentially could have been the gravitational wave source. So the latest results that we've got are shown in the graph on the left. I know it's maybe a little bit technical, but it's just to give you a flavor of where all of this is going. So what we've got is the black curve, which is analogous to the blue one in the slide from a little bit back. So sorry for the change in color scheme, but that's a broad curve and it overlaps with, but doesn't really give much information beyond that about the two vertical bands. The vertical bands are, again, our best guess on the Hubble constant by these different traditional methods that don't agree with each other. So we're still a long ways from being able to answer which of those traditional methods is correct, or maybe neither of them is correct. But we are in the right ballpark, and by adding in the extra information from all the black hole mergers, we've now got the blue curve, which is a bit narrower. So we've improved, but maybe not quite enough to settle the argument on which Hubble constant value is correct. It's tempting to say we look as if we're homing in on the lower value, but there's a number of systematic effects that we need to worry about, that we need to just really keep working hard to improve in the coming years before we can hopefully settle this one. And that, well, let me again just skip one to save some time. That really just brings me towards the end then, because if you want to find out more about all of this, there's lots of ways you can. We've got a LIGO Virgo Kagra YouTube channel. In fact, I haven't mentioned Kagra yet, so let me do that now. Kagra is a detector in Japan, which will be joining us for our next observing run. And in just a minute or so's time, I'll see when that is beginning. But let me also note that you can find lots more about all I've covered on our main LIGO.org webpage. I did our magazine. We publish that twice a year. Very proud of that. There's lots of great articles and stories in there. And indeed, lots of good multimedia, including some of the animations I've shared with you. And you can also follow us on a wide variety of social media platforms. We're not on TikTok yet. We're thinking about it, but we're on all the other big ones. Actually, we're on Mastodon as well now, because frankly, we just weren't sure what was going to happen to Twitter. It seems to have stabilized, but there was a period when we thought, oh dear, Twitter's going to implode. We'd better get ourselves onto Mastodon. So as I said, let me just finish then by saying what comes next. So we've got the LIGO and Virgo observatories, and we've got Kagra. They're being upgraded a little bit more to make them even more sensitive. Kagra's probably got a bit to go before it catches up, but LIGO and Virgo will be even more sensitive than they were during the third observing run. And our fourth run is set to begin in May 2023. So we'll be looking at a further 2 to 3 times increase in the number of events that we detect. The run will last for about 18 months. That means by the end of it, we might have pushing 400 or 500 detections. And what I'll be doing in my copious free time in between being vice principal is working with my colleagues on improving that graph of the Hubble constant to see whether by this completely new method, we can get information about the expansion rate of the universe that, who knows, might just help us settle the question of which of those traditional methods is closer to the correct answer, the so-called Hubble tension. So hopefully I've convinced you that our field has a very bright future. And again, well, watch this space, or maybe it should be watch this space-time for the coming developments in the next years and months. And again, thank you very much for inviting me to come and talk to you this evening. I'll be delighted to answer any questions you might have. So thank you very much.
Thank you very much, Martin. That was a superb talk, really informative as well. I was amazed and impressed by the first slide with all those logos, and I don't think I've ever seen such a collection of logos, and some pretty stellar institutes involved in that as well. So very good. Hey, we've had some questions come in. The first one is from Penny and John Stratton, and they were saying, what is the frequency and power of the lasers used in LIGO?
Oh, that's an excellent question. They're in the infrared range, so I should be able to work that out. You know, E equals H nu and all that. They are not particularly powerful in the sense, you know, you're not going to zap someone and vaporize them. It's more a question of building up the power. So basically what we do is, although the cartoon just had the laser beam bouncing off a mirror and going back, what we actually do is use a technique known as power recycling to keep the laser beam bouncing back and forth within an optical cavity. And in the end, that builds up a total power effectively of several hundred kilowatts. So in that sense, they're powerful beasts, but it's only achieved that way because of this trick of bouncing them back and forth a very large number of times. And what that also does, even more crucially, is effectively increase the path length that the laser beam is traveling. So although the arms are only 4 kilometers long, it's equivalent to having an interferometer with arms which are hundreds of kilometers long. And that's how we achieve the sensitivity you need to get, you know, a millionth the width of a human hair. So it's as I say, a fascinating story in itself. I didn't do the technology justice by trying to squeeze it into just a few minutes. But again, I take my hat off to my colleagues in Glasgow who played a major role in developing all of that technology.
Great, thanks for that explanation, Martin. We've got a question from Ray here, and he says, if gravity waves are not electromagnetic in nature, why is their propagation constrained by the speed of light?
That's a great question, and it's a very deep idea, in fact, which takes us back to James Clerk Maxwell. So I'll send a link afterwards, but myself and Catherine Hammonds, the Astronomer Royal for Scotland, we did about almost exactly a year ago an online lecture for the Wigtown Book Festival, which was about Maxwell, but eventually led on to a discussion about Einstein. We called it Scotland's Einstein, because you could argue, you know, Maxwell is right up there with Einstein and Newton in terms of his achievements. So what did Maxwell do? He developed a theory of electromagnetic radiation. And the way he did it was by looking at and sort of codifying in terms of the maths, some really beautiful symmetries between magnetic and electric fields. But when Einstein came along just a few decades later, he had great admiration for Maxwell's work, but he also had a bit of a problem in a sense because, well, the way that I described it in that Wigtown lecture, let me just briefly do it here. We can, crudely speaking, think of magnetic fields associated with moving charges and electric fields associated with static charges. You know, people might remember doing that experiment in high school where your hair stands on end when you touch a Van de Graaff generator. That's building up static charge, a strong electric field. But Einstein's whole thing in relativity is it shouldn't matter who's moving and who's static. You know, they're different points of view, different frames of reference, but physics should still be describable, whichever frame of reference you're in. Now, that was a real problem for Maxwell's equations, because if you wanted Maxwell's equations to work, to have their beautiful mathematical structure for any observer, the only way you could do it is if the speed of light was the same for every observer. And that, in turn, meant that the speed of light is hardwired into the maths that describes the geometry of space-time, and consequently also is hardwired into the predicted speed of gravitational waves. So it's not a coincidence. It's a very deep manifestation of the way in which Maxwell's equations are saying something very profound about the universe, but they only work in that way if the speed of light has got this special status that regardless of how fast you're moving, you still measure light to travel at the speed of light. Again, I'll send the link to the Wigdown talk. You can find it on YouTube, and people might want to watch that as well.
Great, thanks, Martin. Yes, perhaps Maxwell was the man of the 19th century.
Oh, I totally agree. And in fact, you don't need to take my word for it. Richard Feynman, you know, again, very eminent scientist from the 20th century, Feynman said that, you know, from a vantage point in the far future, he actually went further. He said that Maxwell's equations could almost be seen as the most important discovery of the entire millennium, and never the 19th century. So yeah, one of my missions in life is to get Maxwell's name better known, and his bicentenary is in 2031. I'm a trustee of the James Clerk Maxwell Foundation. So again, watch this space. We really do want to try and make sure that by 2031, a lot more people know just what an important figure in our history Maxwell was.
Yeah, because you sort of have to almost go to university before you hear of Maxwell in physics.
Yeah, which is a great shame, isn't it? Yeah.
You know, and I mean, I didn't really know about him till I actually became involved in Sigma, you know, and which, you know, grief, I was in my mid-50s by that point. So it's, you know, but hey, we've got another question from Ray, and I don't know why he wants a simplistic answer, because the man's a genius, but he says, can you give a simplistic description of what exactly space-time is?
Well, I would argue that I already did with the stretched rubber sheet analogy, but of course that wouldn't be satisfactory in many ways. I readily acknowledge that. It's an imperfect metaphor, not least because, of course, it's only 2 dimensions, whereas space-time, well, does it have 4 dimensions? We're not actually sure. I mean, one of the things we're trying to do with gravitational waves is to develop tools that would allow us to test how many space-time dimensions there are. But, you know, again, as a simplistic picture, it's probably as good as we can do, that what we're thinking of is not something rigid and fixed the way that Newton would have, or indeed probably Maxwell would have, but instead as something sort of malleable, something that describes how objects interact with each other, but it's not a fixed backdrop, it's a changeable backdrop. Now that's, again, the kind of big picture, you know, appealing to the picture of like geometry and stretched rubber sheets. If you drill down into what's really going on the microscopic level or submicroscopic level, well, wow, you know, it's anyone's guess. There's a new Marvel film out called Quantum Mania, I think, today, and I'll be going to see that because I'm a bit of a sucker for the Marvel films. And okay, a lot of the science in it is pretty ridiculous, but it does bring home just how weird quantum physics is. And I think at some level, the nature of space-time we will only properly understand, if we ever do, if we get to grips with the quantum nature of reality. Because on the very smallest scales, we don't even know if space-time is smooth. It could be lumpy, just like, you know, other aspects of quantum physics seem to be. And that could have some bearing on all manner of things, including why the universe doesn't just seem to be expanding, but seems to be speeding up. It could be that that's driven by some phenomena fundamentally to do with the lumpiness of the quantum foam on the very tiniest scales of space-time. So, you know, simplistic pictures are hard to come by in this field, but popular culture has homed in on some aspects, ranging from the stretched rubber sheet picture to the kind of, you know, quantum realm that you get in Ant-Man. So take your pick. But actually, another good place to look, though, is a really nice book that some of you might be aware of. It was written by a physics professor in the US. He used to walk his dog, and he was trying to think of ways to describe space-time and relativity to students. His name is Chad Orzel, and the book is called How to Teach Relativity to Your Dog. So I do recommend it. It's wonderful. It's, you know, very easy to follow the ideas, and it's a really fun read.
Yeah, and Ray says great talk, by the way. So yeah, I definitely agree with that, Ray. So a couple of questions here from David Ray. He says, basically comments, actually, there seems to be lots of black holes collisions, sort of 30 per year. And or he's basically saying, is it just that there are many black holes? So
well, it's a good question. I mean, forgive me for skipping over a couple of slides that were a bit technical, and I didn't want to overstay my welcome. But among the things that we've been doing now that we've got a much bigger sample is really trying to pin down, well, just how many events are happening out there in the universe, every year, every century, whatever. But, the thing you've got to bear in mind is it's a big universe. So, and yes, there are a lot of black holes collisions happening. We've not been able to detect them directly before. Now we can. But it doesn't necessarily mean that they're going to happen anywhere near us anytime soon, because the vast majority of the ones we're detecting are billions of light years away. We got a bit lucky with that neutron star merger, but even it was 130 million light years away, So again, there's plenty of space in which these collisions can happen. Could we detect ones that are much closer to home if they are happening? Well, yes, we could, but we might have to wait a long time. I mean, I remind people in a slightly different context, it's of order 50 years. I hope this is still true. There might have been one recently and I've missed it, but I think it's about 50 years since there's been a core collapse supernova in our galaxy. There are lots and lots of supernovae happening out there in the universe, but within our galaxy, not quite that often. And I guess we've just got to be patient and wait. And believe me, we probably don't want black holes colliding too close to the Milky Way anyway, or at least too close to the solar system, let me put it that way.
No, they are quite scary when they go crash, I would think.
You don't want to be too close to them, that's true.
No, that's right. Final bit of a question from David again here is, are the number of black holes changing with time?
Oh, no, that's an excellent point. And again, maybe if people didn't mind me just borrowing a few minutes of the question time, let me go back to one of the slides that I did skip over. Again, I will try to, darn, I didn't put it in. I must have concluded, nah, that's a bit too complicated, but there you go. I should have had more faith in the Sigma audience asking really good questions. So the seminar I was doing in Wednesday in Edinburgh, we did dig into this a bit, because what we have been able to do by looking at the distances of the events that we've detected, we've tried to not just estimate the overall rate, but tried to estimate whether the rate is changing with distance. And of course, remember, that really means changing in time, because the further away they are, the longer ago the collision happened. And there's pretty good evidence building up now that yes, the rate does change, but in some ways that's not too surprising, because the rate at which stars form changes over cosmic time. And the more stars you have forming, the more potential black holes you will eventually have forming as well. So one of the key challenges is to see whether the information we're getting from gravitational waves is consistent with the information we're getting from electromagnetic radiation from things like the James Webb Space Telescope. So, it's probably too soon to say, but we don't see any strong evidence of a discrepancy yet. But, these are the kinds of things that will keep us busy for the next few years.
Great. Okay. And a question here from George, and he says, where on the trampoline analogy is time illustrated?
Well, on the trampoline analogy, we're reducing it to purely spatial dimensions. It's very hard for us to visualize space-time. Even in Einstein's special relativity, where space-time isn't curved, it's flat. But the traditional rules we learn about at high school of, let's say, triangles, how they behave in flat space, they don't work in flat space-time. Instead of, to use the mathematical names, Euclidean space, you have what's called Minkowski space-time. So the intuition we build up from looking at, flat surfaces and what things would do and what they would look like don't really serve us all that well. In a sense, you've just ultimately got to fall back on the maths, which is a bit unsatisfactory. But hey, that's why we teach this stuff over many years and build up our students' expertise to the required high level. People will probably know, for example, that there are stories about that in Einstein's own education, that he skipped a lot of the maths lectures that he should have gone to. And if he had gone to them, he might have arrived at general relativity years later, a bit more quickly. But fortunately, his great friend Marcel Grossmann did go to those lectures and helped Einstein to fill in the gaps.
It's always handy to have a mate go to the maths lectures for you.
Absolutely. Even Einstein did it that way.
I've got a bit of a question for you myself here, and it's basically what caused you to become involved in LIGO, and when did that sort of thing happen?
That's a great question as well. So you know, I've been around a bit. I studied in Glasgow between 1984 and 1988, and when I was in my third year, our external examiner, who wasn't like examining me because I did all my exams in the final year, kind of different these days, we have exams in every year, but back then, you know, I was just enjoying my third year. The lectures were great, but then we had the whole summer off. But I had the chance to work at the Royal Greenwich Observatory that year, and I heard a few talks about black holes. I got to talk to some of the other researchers, and I also heard about how with gravitational waves, it would be possible in the future, maybe, just maybe, to measure the Hubble constant. So that sparked my interest. I found out a bit more when I went back to university for my fourth year, my final year, because we did a course in general relativity. And, you know, I thought, oh, wow, this is great. I want to do my PhD in this stuff. But in the end, I did my PhD in measuring the Hubble constant just by more traditional methods, using light, you know, the kind of stuff that maybe you've heard me talk about before, or others talk about, like Cepheid variables, supernovae, the so-called cosmic distance scale. So the gravitational wave part of it got kind of put in the background for a while. And I went to Sussex University. I did a couple of postdocs there. And then I got my faculty position back in Glasgow in '98. And in the intervening years, my colleagues in Glasgow who were thinking about building these detectors, well, they'd made a whole lot of progress. They were saying, look, it's still going to be a while, but we think within maybe about a decade or so, we'll have detectors operating. Okay, it took a little bit longer than that, but it meant that what those colleagues did was they said, well, we'd like you to get involved because we're going to have to start learning about the astrophysics side so we can make predictions of how many events we'll see and what sort of events we'll see. So from 1998 onwards, I got more and more involved. It took about a decade before I was like a fully paid up member of LIGO, because I was a wee bit doubtful at first, because I thought, well, yeah, you say you're going to detect them in 10 years, but it might take 30 years. And, you know, what am I going to do while I'm waiting? But in the end, I joined fully in 2008, and it was only another 7 years before the first detection. So got to be patient in this game, but we got there in the end. And my initial interest goes all the way back to the mid-80s.
Yeah, it's a good job we had America to set up all this kit to put these great bits of great devices into, really.
Very true, but equally the NSF realised that it required, you know, a global community to support that. They had the labs, but a lot of the theoretical expertise was in countries like Germany, France, the UK, Australia, and so on. So yeah, it's been great to be part of that. It's almost like a kind of extended global family. And you know, I feel a bit sorry for the students we have just joining LIGO now, because nobody travels as much as they used to. That's probably good for the planet, but it does mean that they don't get to know their colleagues as well as I did during those early years. And I guess it's just, you know, one of the challenges of doing this kind of global science in a world where travel isn't as easy as it used to be.
No, I guess not, but still. Anyway, look, thanks very much, Martin, and thanks for answering all those questions. We'll hand over to Tim now for the vote of thanks. So, and the presentation of the tumbler. So over to Tim. Thanks very much, Martin, anyway.
Hello, Martin. Thanks so much for a really outstanding talk. I hope you don't mind. I've got a couple of extra questions if you've got the time.
Sure, I do need it. So I'll try and be brief because I know you've got other business to cover. But yeah,
well, the first is kind of linked to what you were just telling us about your own career.
Yeah.
We've got a young student in our audience this evening, and what advice would you give to somebody like him who's still at school who was interested in following a career in gravitational wave astronomy.
Oh,
What sort of subjects?
Yeah, great question. So I'll try and be brief, but it's worth just noting, as maybe you know, Tim, and I know certainly others in the call are aware, that for a number of years I've been involved in the redesign of the high school curriculum in Scotland in physics, not across the board. And in fact, I've been on the team that review the advanced higher paper. So I've done the 23 advanced higher paper, but my lips are sealed. I can't say anything about that one. But yeah, it's been a real pleasure to see the way in which some material related to all of this has found its way into the higher and the advanced higher. So if your audience member is studying physics at school, then frankly, that's a great start, because you're now getting to learn about a lot more about gravity and astrophysics than you used to when you study the higher and the advanced higher. Beyond that, then maths is pretty important. And, I think it would be foolish for me to pretend otherwise. Lots of people I meet are passionate about astronomy. They love astronomy, but then your heart sinks when they say, but I really don't like maths and I'm no good at it. And you think, well, that's great that you can pursue astronomy as a hobby, but pursuing it as a career is going to be pretty hard unless you're into the maths. But that said, a project like LIGO draws upon such a broad range of skills. You've got engineers, computer scientists, chemists, material scientists. So it doesn't have to be astrophysics. But if astrophysics is the thing that's your audience member's primary passion, then, studying physics and maths at school, studying physics and astronomy, or maths and astronomy, or some combination of them at university, that's how to do it. And in a way, don't worry too much about focusing on gravitational waves early on, because a degree at uni will give you a very broad introduction to astronomy, and then you can focus a bit more later on. So that's what I would say.
That's great. Well, the student in question is called Gabriel. He hasn't been too well, actually, but it's nice to see that he's online.
Well, if Gabriel would like to get in touch, I'd be happy to follow up. So by all means, pass on my email if that's helpful.
Lovely, thanks so much. The other question, back in the days of the space race, when lots of billions of dollars were being spent, justification for the space race was, there are lots of spin-offs. And of course, there was the myth of the non-stick frying pan, yes, which Teflon had been around for 30 years before. But anyway, what I was wondering is, are there any current spin-offs coming out of the LIGO technology? Yes, not just hardware, but also software.
An enormous number. So on the hardware side, there's things like laser stabilization, which we have to do incredibly well. That feeds into some of the processes used in things like laser eye surgery, or even in how you get the laser stable to operate your DVD and CD, although that's a bit old school now, I suppose, compared with streaming. And then there's also some really very striking spin-offs, which are just that classic example of, cross-disciplinary coming about just from random discussions. So one of my colleagues, Stuart Reid, who's now at Strathclyde University, is still very active in LIGO, but is also very active in bioengineering, because our ability to control the frequency of, oscillating systems and to understand the physics of oscillating systems allowed him to develop a technique for stimulating the growth of embryonic stem cells. And there was a wonderful feature on BBC Scotland News about it a few years ago, where they described this as nano-kicking, because the cells are just like nanometers across, billionths of a meter. And you don't have to kick them very much to stimulate them, but you've got to do it at just the right time and with just the right frequency. And that control has allowed Stuart to develop ways in which you can grow stem cells to, to contribute to bone graft surgery, all sorts of things like that. And yet you mentioned software. So there's a lot of software stuff as well. I think chiefly it's a real sort of virtuous circle, because we're doing our best to pick up on a lot of software developments from outside our field and apply them, but some go in the other direction as well. And it's often to do with things like artificial intelligence and neural networks, because we've got to process a heck of a lot of data in a very short time. And in some ways, it's like the classic AI problem, complicated images, how can you tell what the structure embedded within them is? And I should also note that in my current role, you know, Clark has said it, one of the things I'm responsible for is the sort of academic integrity of all of our degrees across campus. And I have to say, we're getting a little bit worried about ChatGPT. But again, it's helpful that because I know about machine learning through my research, you know, that at least brings a bit more background knowledge to understand how it might be impacting our students' exam essays and that sort of thing. But yeah, that's just a few examples. There are many more, but
excellent.
I hope that answers your question.
And I'm sure there'll be more in the future. Martin, it's been a fantastic talk, as always. This is your 7th talk to Sigma, not to mention, of course, the other situations where you've been of help to us. When I was looking back through my historical records, I was looking back to 2009. I don't know if you're still reeling from the event of the Scottish Solar System project.
Well, I remember it very well. Yeah, absolutely. It was a real pleasure to do that, and participated.
I always remember receiving Chiron,
Yep.
a small pebble, which was our contribution. And I was talking to my fellow president Bill Leslie, who, as you recall, he was the first member of Sigma, I think, that you met.
That's right.
He was reminding me that he was at a meeting for the Murray Science Festival way back when, and Lindsay Fletcher, one of your colleagues, was giving a talk, and he asked her a question, and Bill said that she didn't know the answer, but she said there's a chap at the back called Martin Hendry who'll be able to answer it. So Bill came to you and then twisted your arm to come and give us a talk, which was back in 2003, I think, was your first talk.
Yeah, that's wow. Thank you. It's nice to go down memory lane like that. See, Lindsay I've known throughout my whole career, and we were undergrads together as well. You know, one of my longest friends. And yeah, her auntie lived in Elgin. I'm not sure if there's any relatives still around, but
that's right.
Very nice to be reminded of that too.
That makes this a 20th anniversary, doesn't it?
Yep, that's right.
Yes,
yep.
Yes. And the other anniversary, and we run on our newsletter, we run a monthly anniversaries tables, just to remind people what's happened. I had a quick look before I came online, and there was tomorrow is the birthday, the day that John Brown, Professor John Brown, your colleague, was born, 4th of February 1947. God rest his soul.
Yeah, we miss him very much, and I'd forgotten it was then. Yeah, indeed. So thanks, Tim. That's a very appropriate point to note as well.
Yeah. So I thought, when I was thinking about it, I thought it's really nice. You're giving the talk today, and it's his anniversary tomorrow. So there we are. Well, as you'll know, having been to so many talks, we have a gift for you, and it won't come as much surprise to say it's another tumbler. Now, for those who weren't at Sigma in the early days, I think the early gifts would have been things like glass paperweights. I don't know if you've ever had one of those.
I have indeed. I've still got it on my desk. Yeah, that's right.
It'll be worth millions in years to come. You'll be able to sell it on eBay. But you'll have. I certainly have a few tumblers, and. We've always had a bit of a humorous rule that once you get 6 tumblers, you'd get a decanter. But the catch, as you know, because you've been so many times, is that they all have to be the same type of glass. And unfortunately, we've changed just in time for 2023. We've changed the design of our tumbler, so you won't get that exact size, but you'll get a slightly different one, but one to add to your collection. And I hope that you'll add many more in the future, Martin, because you're a real friend of Sigma, a real supporter of what we do. And can I thank you so much for the talk that you've given us this evening.
Thank you very much, Tim. And thanks
back to Pete. Thanks a lot
to everyone. It's my pleasure. I'm very honoured to be seen as such a friend of the society. That's very much how I feel too, and I look forward to meeting again in person.
Yeah, I'm sure we'll get around to doing it again soon, Martin. We'll get you down here or up here. Yeah. I'll just say, because we know one second what Tim said there. Fantastic talk. I did say in the newsletter to everyone not to miss this one because they will, because if they haven't seen you before. So, but thank you so very much, Martin. It's been great to see you again.
All the best, everyone. Take care.
Okay, you're quite welcome to stay for the second half, but I know you've been busy all day, so I'm
off to get my dinner now.
I don't blame you. Thanks again very, very much. Okay,
Bye-bye.
we'll see you soon. Okay, everyone. You'll notice that the chat's back on now, so you can have a talk to everyone. Just remember, if you're going in the chat, just to change your little drop down to everyone. I think it's preset to just panelists and hosts. So if you want to talk to the other members, just click that drop down to everyone. That'll be on during the break. So we'll head out to the break now. We'll have a 10-minute break, so we just get set up for the second half. We're running a little bit late, but that doesn't matter. As I say, it's a full moon out there. We're not rushing out to get the telescope tonight. I think it's cloudy anyway. And I say we'll be back in 10 minutes for the second half with I've got some members' photos. Got one coming from Ken Kennedy from Dundee actually as well. So we just look forward to seeing that one. So we'll say 10 minutes and we'll see you back here. Okay. Thank you, whoever that was. I'm off.
Okay, we're in there, are we? Okay, good evening all. Welcome to February's Murray Sky at Night. As we've got new members tonight, I'm going to use the first part of the talk to introduce our new members to the night sky. And I'm sure this will be a good recap for everybody else who've already heard we're about to cover. So I'll start by introducing Stellarium. So as you can see here, this is like a planetarium program you can get for your any computer, mobile phone, laptop, tablet, sorry. So it's really handy. You can take your tablet or your phone outside and use it and hold it up to the sky, and what you see in the sky is what you're seeing on Stellarium. So it'll show you what everything is. One other thing of note is on your phone and tablet, you can actually change the color of the screen. I can't show you on here because it's on the PC, but you can change the color so it's a red screen, so it won't interfere with any of your night vision. I think there's a charge for Apple products, as it always seems to be. I think it's $16.99 if you want to get the upgraded version of the Stellarium Mobile, it's called nowadays. But I think it's still worth its weight in gold, really. It's my favourite one. I know there's plenty of others around, but it's the one I use and one most of us use in Sigma. It's really good. So I've set it here to the middle of the month, with the moon being out of the way, so it kind of helps to see what you see in the sky. So as you know, we're in the Milky Way galaxy, and if you look up, you can see these bright milky patches. And this over to the northwest here is looking towards the core of the galaxy, and come over the top overhead and right down into the other horizon. That's us looking through the center, or the disk, if you like, of the Milky Way. Called milky because of the color. It's like spilled milk. And the milky part is actually basically out of focus stars. There's estimated to be about 100 to 400, say 300 billion stars in our galaxy. And there's about 5,000 visible in our hemisphere. You can see as you look overhead, there's a kind of dark bit. That doesn't mean there's no stars there. It's just dark matter and space dust getting in the way, blocking the light. Otherwise, it would just look like that all the way across. So everything you see with the naked eye, when you look up at the sky, everything you can see is in our galaxy. There's only 3 things that you can see with the naked eye outside our galaxy, but 2 of those are in the southern hemisphere. That's the small and large Magellanic Clouds, which are galaxies in their own right. And there's one other thing that you can see in the northern hemisphere, which I'll point out in a little while. So the Milky Way is 170 to 200,000 light years across, and the solar system that we sit in is 27,000 light years from the galactic core, which I pointed out over here. And we're on the inner edge of what is called the Orion Arm. So as you can see, some of the stars form patterns known as constellations. There's 88 that we use, constellations. And of course, these constellations, these shapes are only visible from our perspective here on Earth. If you got on a spaceship and disappeared off in one direction and you look back, you would see the same stars, but they wouldn't be in that shape or form, basically. And all the stars, something else to bear in mind, all the stars are at different distances, pretty much. So you'll have some brighter stars, which are larger, but they might be closer. You have small ones, which might be bigger than this one, but further away, that kind of thing. You know, they're all different distances. So none of these constellation stars are on the same plane, if you know what I mean. They just look like that from our perspective. There is some artwork as well. I'll stick up for you. So you can see we've got like Leo the lion, Cancer the crab, Gemini the twins. And of course, these are signs of what's known as a zodiac, 12 of them. There's actually 13, but they use 12 because it's quite handy, one for each month, signifying the journey of the sun through the year. It spends roughly a month in each of these constellations. So the sun, with us following it, travels around the galactic center, and it takes 230 million years to go around the galactic center. So how do we find our way around the night sky? Let's clear some of this away. So we use what we call star hopping. So what you can do is you only need to kind of know one or two constellations to start with. And if you use them as a starting point, you can work your way around. So what I like to use is this one. I'm pretty sure you'll recognize it as the plough. So this is actually what's known as an asterism, which means it's a shape that's part of another constellation. And this is part of Ursa Major, the Great Bear. And using these stars, I always think of it like a chip pan, the plough. So you've got the handle and you've got the bowl, if you like. If you take these two stars here, follow up, the next brightest star you'll find almost directly overhead from where we are is Polaris, the pole star or the North Star. Very handy for us in the Northern Hemisphere because it's nearest the North Celestial Pole. So those in Australia are not quite so lucky. They don't have a star that's near the South Celestial Pole, so they have to do other methods. But we use this as amateur astronomers, we use this to align our telescope mounts. And by doing that and having motors connected to the mounts, we can offset basically the rotation of Earth and keeping any targets that we have, for example, stars or galaxies or planets, we can keep them stationary in our telescope, which is good for if you just want to study it or if you wanted to do some long exposure images or astrophotography. So if I just move this around a bit. So go from the plough here through Polaris, just across the other side of the sky. We see this kind of W shape of stars. This is Cassiopeia. So Polaris, coincidentally, is it's in Ursa Minor, the little bear, and there's Cassiopeia. And Ursa Major over here that I just spoke about. So there we've got three targets straight off that you can find straight away. Now I mentioned there was something outside our galaxy which we can see with the naked eye. And an easy starting point, now you've found Cassiopeia, is to use this. So if you take the second V that makes up the W of Cassiopeia and come down about 2.5 times the height of this V. You'll see just to the right here, there's a little fuzzy patch. This is Andromeda Galaxy, M31, or Messier 31. And this is our nearest large galaxy, part of our local group of galaxies. It's a spiral galaxy, it's twice the size of the Milky Way, and it's actually 2.5 million light years away. So the light you're seeing from that is 2.5 million years old. So of course, it might not be there now. You'd never know unless you waited another 2.5 million years to see, would you? So good luck with that. One of the interesting things about the Andromeda Galaxy, now as Professor Hendry said earlier on, the universe is constantly expanding. Everything's moving away from everything else, or as he called it, red shifted. Andromeda Galaxy is actually blue shifted, which means it's moving towards the Milky Way. So eventually there's going to be a merger. Some say collision, but the chances of anything colliding, because everything's so far apart, not impossible, but reasonably unlikely. But nothing to worry about just yet, because it's not going to happen for another 4.5 billion years. And it's expected to form a giant elliptical or lenticular galaxy. So how far is a light year? I said it's 2.5 million light years away. So light year is a measurement of distance, and the speed of light being 300 million 300 million meters a second. You multiply that up by 60 to get a light minute, then another 60 for a light hour, another 24 for a light day, another 365. Multiply all them up, and you get round about 10 trillion kilometers. So that's how far light travels in a year. 10 trillion kilometers or 6 trillion miles. So you multiply that by 2.5 million light years, and that's how far away Andromeda Galaxy is. So it's very far away. And while you're on this, if you stick a telescope on it, you'll see there's a couple of extra things around about it. There's this fuzzy patch here is M110, Messier 110, and this one here M32. So there you're picking out 3 galaxies for the price of 1. One thing I forgot to mention with Cassiopeia. Now, I said Cassiopeia. With Cassiopeia, Cepheus, Ursa Minor, Ursa Major, and Draco, I believe. Yeah, Draco. These are all what are known as North Circumpolar stars. So as long as you're in the Northern Hemisphere, these 5 constellations will always be above the horizon. Okay, so that's a little introduction to stellarium for you. I'll show you another couple of things as we go along. What I'll do now is I'll go through my usual little chat on the kind of photo opportunities, what the planets and moon are up to through the month. Get the date set. Go to 16. Yeah, go to the. So this was earlier on this evening. It's not going to change much tomorrow, actually. So looking to the south, which is obviously where all the planets sit. The sun's just about to set there. We can see as we move across the sky, Saturn's getting very close to the sun now. We have Venus coming across to the east. Jupiter, Uranus sitting in here. Oh, go away. There we go. Uranus, Mars, and an almost full moon has risen as well just before the sun sets. Going to tomorrow night. Let me just go to F5 tomorrow night. So Venus is about to set. This is 5:30 tomorrow night. And in amongst here we have Neptune. Oh, got it, Neptune. So Neptune's in here. For you to see, moving to the 6th. Oh, a little bit later. We have a full moon is going to be just 4.6 degrees north of Regulus in Leo. And where am I at 9th? Let's go back to here again. Now Neptune is going to be passing very close to Venus if we go through towards the 17th. On the 16th, Saturn's basically out of view at the minute. On the 16th, though, it's going to be in opposition, which means it's, it's superior conjunction, opposition. It's going to be superior conjunction. That means it's going to be at the other side of the sun, so you definitely can't see it. I wouldn't even bother trying to look for that just yet because it's just not going to be visible. The 22nd. 22nd, we'll get Neptune, Venus, first quarter moon, I believe, and Jupiter all together, just about to set in the southwest. So if you want to try and capture any of these, it's going to have to be not long after sunset. But of course, please don't be taking any optical equipment out and pointing it anywhere near the sun, because you may end up permanently blind or doing yourself some serious eye damage. So make sure the sun's well out the way before you start pointing binoculars in this direction. Going to the 25th, going to have, let me just zoom in a little bit here. Let's keep it easy to see. So the moon's just going to be within 1.3 degrees of Uranus, and that's going to be a first quarter moon. And the 26th, let me just move this now, the 26th to 28th. So the 26th, the moon's going to be just to the south of the Pleiades, and then passing by Mars. And for those with a keen eye, you might have noticed that Venus and Jupiter are getting a bit close here. So what I'm going to do is, because our next meeting is going to be into next month, and the 28th is the last day of the month, I'll just show you that. Let me just put this to here. So at the beginning of the month, beginning of March, you're going to have Jupiter and Venus right next to each other. And then the second, they're going to be quite close as well. And that takes us to 3rd of March, which will be our next meeting. So that's pretty much the sky. So I'm just going to finish off to mentioning the comet. Now, Pete mentioned it earlier, and you saw the pictures. So for those unaware, comet C2022 E3ZTF was discovered on the 2nd of March last year, and it was at a magnitude of 17, which means it was very dim. So it passed perihelion on the 12th of January. So that's its closest point to the sun. And it was at a distance of 1.1 astronomical units from the sun. And after that, it started moving a bit more swiftly through Bootes into Draco. It became a circumpolar object and a binocular object all night. It was closest to Earth 2 days ago. None of us have been able to see it because of the clouds, unfortunately. And it was in Camelopardalis, and it was only 0.29 astronomical units, or 27 million miles from Earth. So it's now moving close to Capella in Auriga. Let me just find it for you and show you what it is. Right. Now, this is kind of low on the horizon. What I'm going to do deliberately, I'm going to spin this right round. Oh, wait a second. There is a reason for my madness, honest. I get stellarium to play. Yeah, I want it about there. Okay. There's a reason. Right. So it's going to move towards to Capella on the 5th. And then it's going to move through Auriga. I'm going to put the boundaries up. Right. What I'm going to show you is how to plot. Tell you what, let me just bring this back around far away. I'll quickly show you how to plot the path of an object. So this comet, good example. So in Stellarium, if we go here to the astronomical calculations window, click twice, and you've got all these tabs across the top. If you click on the ephemeris and go in here to find the comet, and then you can select the dates. So we've got the 3rd of March. Hold on. That's why it's not where I thought it was going to be. I'm in the wrong month, aren't I? Let's go back. Right, that explains it. I was wondering why it was wrong. Right, let me go to now-ish, 9:30. Right. Now it's looking better. Right, back to astronomical calculations. Ephemeris. Okay, so from tonight, 5:30, yeah, close enough. I'm going to take it to the end of March. So we'll go to the end of March. And you can select the time steps on it. So what it will show in the plot when it comes up. I've set it to 5 solar days. Otherwise, it's just going to be really crowded. And you can show it as a line, markers on it with dates. And then you go calculate ephemeris down here. And then if I take this out of the way, what's happening here? This has gone wrong. That's not it. I picked the wrong comet. Let me just see again. Third of March. 3rd of March, 3rd of February I want, isn't it? Dull. Right. That's more like it. There we go. So this is where it is now. And it's going to move, if I move the date through the month, you can see, so every 5 days, so on the 8th, it's going to go through Auriga, move into Taurus. Of course, I've set it to 5-day intervals on the markers, but I'm only going up 1 day at a time. So there we go. So that's the journey of the comet through the month. Hopefully you'll get a chance to see it now. If I take it back to the top, let me just start again here. Oh, is it going? Right, I've got the comet again. If you look up here, the magnitude, it's showing a magnitude of 5.1, so it's naked eye visible at the minute. As it approaches 6, you kind of need to be in a really dark sky area or get some binoculars on it. But as I move through the month again, if you watch the magnitude, you can see the magnitude's creeping up. So it's getting dimmer and dimmer as time goes on. So hopefully some of these clouds will disappear and we can get out there at some point and have a look at it. You can get further information. You can get plots similar to this on Heavens Above. You can get a daily update of it, so you can see exactly where it is. And when you go to Heavens Above, it's good to create an account, because then you can put in your location and save that in your account. So every time you log in, it'll show you on the website what it looks like from where you are, and not in London or somewhere. And I also pointed out last month in the sky.org, in the-sky.org, you can input your location there as well. You can. I found Elgin was the closest to me in Lossiemouth. It didn't find Lossiemouth, so I put Elgin, UK in, and that gives you up-to-date information. You can get 3D graphs and all this kind of thing going on there as well. So that's just something else to look at. The links for both of these are on the club website, so feel free to go on there and look for the external link page on our club website. And that's about me for this month. I think I'll see you all again next month.
Okay, Mick, thanks very much. And that's a great introduction for people who've never used sort of Stellarium before, any desktop planetarium. And it is a really, really good program. And if you want to learn the sky prior to going out, it is one of the better ones to get out there and get it downloaded and to use it. Okay, we'll finish off with a little bit of the club news. I'll just put some light on here so you can see my ugly mug a bit better. Yeah, as I say, the comet hunt we planned didn't go very well because it was either too cloudy or it was too windy, or when it was, it didn't clear for very long, and then it was really too cold and too late at night. As I say, but as Mick said, the best thing to do, I've got it now. I've got a pair of binoculars by my back kitchen door, and if it clears at all, just pop out, point it in the area where the comet's going to be. That's why these charts are so good. Point it into the area where you think it's going to be, and once you notice it, you can't miss it. Honestly, it look a large grey fuzzy blob. But the other night I managed to get it in my bigger binoculars. I got a set of 25 by 40 by 100s, and it was looking quite good in that. But it was very, very short-lived. The sky wasn't that good. The seeing wasn't that good. But I've seen it. That's the main thing. But you just got to be, get out there and have a look when the clouds break. But we are planning more of the observing sessions. The SOG, the Sigma Observing Group. I actually wanted to make the acronym SOGgy, because most times we go out, it's been raining beforehand, but I couldn't think of any, any words to make up the G and the Y. So if you've got any ideas, let me know. But it isn't any good. SOG's good because it fits quite well into the WhatsApp. SOG is too long, into the WhatsApp name. But so really, really want to thank Ray, Mick, Stuart, Rich, Jackie and Rob Eady, John and Penny Straighton, and Tim for coming on to the SOG group, because having more people is going to make it a lot more easier for us to get out there and sort of organize these observing sessions for you. When it's just down to 2 or 3 people, someone's ill, someone's busy, it makes it more, makes it difficult. But having so many people there who's going to get there and put this on. We should start getting more observing done. Let's put it that way. So all we need now is the good weather. You should all be receiving your go, no go notifications via email and WhatsApp. If you're not, let me or Mick know and we'll see what's happened there. Talking of WhatsApp, I was quite skeptical of WhatsApp when it first came out, I must admit. Maybe it's me age, I'm getting older, but but this WhatsApp, the WhatsApp group is really good, because as soon as someone says, "Oh, the sky's clear," it goes mad and everyone's going out. "Oh, yeah, I've seen it. You've seen it. It was here." And if you're not sure, have a chat, and if you're not sure you've seen it, there was one person on there. So I don't think I've seen it, but there was something fuzzy. I said, "Well, that's it. If it's not a star you're seeing, that's what you're seeing." And it's a great way to get an instant, right, okay, we're going, the no-go notifications will also be sent out by email as well, so you probably will sort of receive them twice if you're on the WhatsApp group. The reason is some people aren't on WhatsApp and some people never will be, as I know, so we're still keeping the email system going. Next month's meeting seems like an interesting one. What makes planets habitable by Patrick Barth from the University of St Andrews. This and that meeting will actually be our last Zoom meeting. I would think we might have one more yet later on, but officially next month is going to be our last Zoom meeting. We'll be back to physical meetings all the time after that. Yeah, so that's on the 3rd of March 2023. And I say that one's on Zoom, but then it'll be the last one. Don't forget the telescopes we've got. Please come and get these telescopes. Actually, I think Jackie and Rob have got the Skywatcher at the Dobsonian at the moment. But obviously, if you want to borrow one of these telescopes, please do. We've probably only got 12 weeks left of dark nights. You know, reasonably early dark nights, and probably 8 weeks of reasonably early dark nights. Once we get into the mid of April, then we're going to lose the darkness. So if you want to use the telescopes, let us know, and we'll get one of them out to you. So they're there for your use. If they don't get used, they'll just go dusty. Right, so say Sigma on YouTube. All our Zoom meetings gone on YouTube. So if you missed part of this tonight or any of the other ones, just pop over there. This one will be up probably by Sunday evening if I get the time to edit it and get it all up and ready. But I'll send the link out once it's up and done. But all our Zoom ones are there. So any new members, if you want to catch up on any of the talks that you haven't seen previously, they're all up there, and the link for that is in the newsletter. And also the new members, if you, or not the ones who've joined, but anyone first time visiting and wants to feel like joining Sigma, it's easy to do so now. Go over to our website, go with the membership page, and there's actually a link there where you can put your details in, and all the information is there of how you can do a bank transfer to pay, to pay your subs. And if you've got any friends who want to come along, please let them know, and we can always send them the link for next month, or just bring them along to Lambride in April. Okay. And if you got anything from me, just you know where I am. Some of you, most of you know where I live now, actually. But so you can always get hold of me on my email address, chair@sigma, or just pop something in the info. Okay, so I think just want to say thanks very much again to Professor Martin Hendry, for the fantastic talk. I told you in the newsletter it would be a good one, and it didn't disappoint. Rich for handling the Q&As, Tim for your vote of thanks. You do us proud every time for that one. Mick for your More Sky at Night, a great introduction to stellarium and how to find your way around the nighttime sky, which for new people who've not done much astronomy, that is where you want to start. Learn a few of the stars, some of the constellations, and just try and find them when you go out at night. And I say for you good selves for coming along, and we will see you in March. Well, hopefully we'll see you under the starry sky sometime. Hang on. John Penny straight and said, how about a talk about basic astro? Right, okay, I'll come back to you on that and see what we can do. But thanks everyone for coming along, and we will see you in March. Okay, stay well, everybody.